Hi, welcome back for part two. In part one, we took a look at creating confidence intervals in the very likely situation where the information that we were given was sample information. That is, we had a sample size, a sample mean, and a sample standard deviation. Well, so we're going to start by taking a look at an odd situation where we would be estimating a population mean and somehow we would know the population standard deviation, which on its face does not make any sense. I don't know how someone could know a population standard deviation if they didn't know the population mean, because the math to find the standard deviation first requires that you have the population mean, because it's in the calculation for the standard deviation. Okay, but let's just dispel reality and pretend that this situation was possible. Well, since you know a population standard deviation, you're not going to use the t-distribution. You would just use the standard normal distribution. You would get a margin of error formula that would look like this, where this is a z right here, and this is a sigma, whereas before it was a t and an s. So we're looking at using a normal distribution because we know a population standard deviation. Okay. All right, so let's go ahead and take a look at an example of building a confidence interval for the mean if you somehow magically knew the population standard deviation. Here I've got a data set, and it's asking me to create a data using the 15 birth weights below, for which n is 15, sample mean is 30.9, hg's, what is that? H is hectograms? Okay. I don't do metric much, but that just seemed weird to me. Why wouldn't you just call it in grams or kilograms? But okay, whatever, hectograms. Construct a 95% confidence interval. So I'm creating a confidence interval with a 95% level of accuracy. And I'm supposed to somehow magically assume that the population standard deviation is 2.9 hectograms. So I've got a data set where n is 15, where the sample mean is 30.9, and where the population standard deviation is somehow known to be 2.9. And again, these are hg's, hectograms. Okay. Now, because this is a population standard deviation that is known, this doesn't matter. A moment ago, last video, when we were doing the t-distribution stuff, when we were finding confidence intervals where we did not know the population standard deviation, we just had a sample standard deviation, we cared about sample size. If you somehow magically know the population standard deviation, sample size then becomes irrelevant. And you can just work this calculation regardless of the sample size. Right. Now I'll show you really quickly how to do it by hand, and then we'll do it on the calculator so you can make a decision. Okay. So E, the margin of error, is going to be that critical value, z sub alpha divided by 2, multiplied by that population standard deviation divided by the square root of the sample size. Since this is a 95% confidence interval, that z is 1.96, multiplied by 2.9, divided by the square root of 15. So over to my calculator, 1.96 multiplied by 2.9, and then divided by the square root of 15. And I get that my margin of error would be, since all the data is to one decimal place, 1.5 will be my margin of error, and these are hectograms. So then I could say that my 95% confidence interval is 30.9 hg's plus or minus 1.5 hg's. Or I could take that 30.9, subtract off that 1.5, let me try that again. 30.9 minus 1.5, and I could get that it's from 29.4 Hgs to 32.4 Hgs. And that will be calculating it by hand. Now, that actually goes pretty quickly if this is nice, which makes this a known value. Right? I could do the exact same thing on my calculator. Let me show you how. Right? I'm going to go back to my stats, over to my tests, and this time I'm looking for the confidence interval based on z-scores, so z-interval. My population standard deviation is somehow known to be 2.9. My sample mean is 30.9. My sample size is 15, and the confidence level that I'm supposed to work with here is 95. I calculate, and you'll see I get my 29.4 matches here to 32.4 matches here when rounded to that one decimal place. All right. I do want to show one other thing. Suppose that this wasn't told to us and that we just had this data set, right? I can still do this, and let me walk you through how, right? So if I don't know this and I want to create a confidence interval, I can still do that. Step one is going to be to input the data into a list. So just like we did before when we wanted to run those one variable stats, I'm going to go to stat, I'm going to go to edit, I'm going to put that data in. So it's 33. I'm going to pause. I'll come back when it's okay. So I got all the data put in to the list. And now I'm just going to run that z-interval command again. So back to stat, over to tests, down to z-interval, right? But this time I'm going to highlight data. Okay. I'm going to tell it the standard deviation is still 2.9 because somehow I magically know the population standard deviation. I'm going to tell it I hid the data in list 1. I put a 1 there for frequencies because it's just a single list of data. There's no frequency distribution information. I still want a 95% confidence interval, and I'll go ahead and calculate. And do you see how I essentially get the same values this time? Now, I know there's at least one person who's been watching really, really carefully who'll say, hey, wait a second, those numbers are slightly different. Yes, they are. Because when we did this by putting in the stats, when we did the stats here, we used 30.9 exactly. When I put in the data set into the calculator, look at the X bar that it's using. It's 30.8666. So that 30.9 was a rounded value. And because it was a rounded value, it was going to make this answer be slightly different. Now, when rounded, it'll still round the lower limit correctly, but it would round that upper limit to 32.3 rather than 32.4. That's not going to be an issue. The tolerances are set in such a way in the homework that if you were off by 0.1 on this problem, it wouldn't change a thing. Okay? So this technique of putting the data in instead of the statistics in works for z intervals. It also works for t intervals. Okay? All right. So just remember something. What we just did is authors usually, when they write their books, they say it is a rare situation. I would argue that it is an unrealistic situation. Knowing a population standard deviation and not knowing the population mean is not a situation that I can wrap my brain around. So Z intervals, while the math exists to create them, they are not a realistic thing. We should really think about it as more of a confidence intervals for the means are going to be T intervals in almost all situations. Okay. All right. Remember the question last semester or last section about how big should the sample size be to make something happen? We got that question here. How big should the sample size be? Well, if we did the same logic as we did last time, we can solve that margin of error formula for n, and it turns into this. Now, here's the one thing that's different, right? This is building off of that sigma is known formula. So this z sub alpha divided by 2 that we're doing here, if you know your population standard deviation, then that is going to be those things like the 1.645 for a 90, the 1.96 and the 2.54 for the 99, the 5 and the 99. If you don't know your population standard deviation, and remember, the whole idea behind finding the sample size is you haven't sampled yet. And if you haven't sampled yet, you wouldn't know a sample standard deviation, right? That how would you make this thing work? Well, you would estimate both your, you would use the z-score still, but you'd estimate your population standard deviation by using one of those rules. Most likely we would use the range rule of thumb to estimate the standard deviation by taking the range and dividing it by 4. So we'd say, oh, estimate this by the range divided by 4. Right? Another way you could do it is you could just start sampling and just get the first few values, calculate a sample standard deviation off of those, and plug it into the formula and see what you get. Or maybe you could find some earlier data that could give you a reasonable estimate for it. Okay. Most likely you would do something like this, right? You'd say, what's the range of this data? Okay. Now, all three of these are crude approximations, so we're going to get pretty big ends, but that's okay. We'd rather sample too many than too few. Sampling too many just makes our margin of error too small. Let's look at this in practice and see what it means. Okay? All right, so assume that we want to estimate the mean IQ score for a population of statistics students. Right? So we want to estimate a mean for a population of stat students. How many students, how many, so we're counting how many, must be randomly selected if we want a 95% confidence that is within 3 points. Okay? So let's see. I want my margin of error to be within 3. I want my confidence level to be 95%, which means that my alpha is 0.05. Now, my formula says that n will be equal to, let's see, n will be equal to, what is n equal to? N is equal to the quantity z sub alpha divided by 2 times your population standard deviation divided by your margin of error squared. Okay, so let's take a look at what we got here. I've got this. That's going to give me that is 1.96. So let's see. So I know that n is equal to the quantity 1.96. I know that this is 3, so 3 is going to go there. 3 downstairs. I know something's going to be squared, but I don't have this. I don't have my standard deviation. So what am I going to do? Well, I've got to estimate it somehow. Right? I've got to estimate a standard deviation for a population. Okay, so I'm going to go back up here and look at my options, right? Well, I could use the range rule of thumb, but I can't here because I honestly don't know what the range of IQ scores are, right? Well, I could start sampling. I'm not going to do that because I don't have access to that to make this problem work right now. So I'm going to estimate it. So maybe I'll go online and Google and say, well, hey, what's the standard deviation for an IQ test? And the standard IQ test has a standard deviation that is set to be about 15. Now, I don't expect that you would know that, but I'm just showing you an example of, well, some earlier study, some other data set, says it's about 15. Right. Most likely, you're going to end up doing this kind of thing or this kind of thing. If you have a scenario, you would use the first one, I guess I'm saying, is if you have a scenario where you know the range. If I know that my soda cans can't be off by more than an ounce, I would know the range. If data was provided to me ahead of time. Right? At this point, all there is left to do, though, with this problem is just to plug it in and grind it out. So I'm going to take that 1.96, I'm going to multiply it by 15. I'm going to divide that by 3, and then I'm going to take that value and square it. And then I'll round that up and say, hey, we need 97 people in our study. Okay. All right, this brings us to the end of section 7.2 and also to the end of chapter 7. I hope you enjoyed it. It should have been a quick one compared to last week. Have a great day, and I'll see you back here for chapter 8.